To tonight's Dementia Researcher Salon Research Showcase. I'm Adam Smith from Dementia Researcher, and thank you very much, all of you, for joining us. Today, we're exploring a really important question. What can music reveal about how the brain adapts to aging and neurodegeneration, and how can mathematics help us make sense of all those changes? I'm delighted to be joined by the incredible Dr. Sarah Faber, who is back again, who's been with us in the salon before, from Simon Fraser University. Sarah is a computational neuroscientist whose work brings together neuroscience, music, and quantitative modeling to understand how the brain networks reorganize over time. In this session, Sarah's going to share how music-based approaches combined with mathematical modeling can uncover patterns of resilience and vulnerability in the aging brain. As ever, with our salon showcases, for those that are new here or haven't joined us before, Sarah will present for about 20 minutes. We're all going to listen very carefully and then come up with our hardest possible questions to put her on, to keep her on her toes. But no, not really. But we will have plenty of time for questions afterwards and for discussion as well, should this also be your field of research. We'd love to hear about that as well. But that's enough from me for now. Thank you very much, Sarah, for joining us again. And I'm going to hand over to you.
All right. Well, thank you so much for the welcome. And you store glasses, yeah?
These ones.
There you go.
I'm getting. This is a sign of my aging. All these ones. I have two different pairs here. This is a sign of my aging, but I can't see close up while I'm wearing my glasses anymore. It's incredible. I'm told it's how your brain and eyes age, so I do, but not right now.
Amazing. All right. Yeah. So that's a really useful and humbling knowledge that the Superman thing would absolutely fool me, because I was just like, oh, do I know? Like, you seem awfully familiar. It's just like, yeah, we know each other.
I've lost a bit of weight as well, so that could also confuse people. So that's my face is rather thinner than when we start doing these things.
This is a great welcome to a talk on aging.
I know, absolutely. I'm going to shut up now. Over to you.
Thank you so much for the lovely introduction and for the invitation back. I really like this this community full of people, and just the concept of a salon is just great. It's like, yes, and accommodating with the time. Like, it's noon where I am on the west coast of Canada. It's 8 p.m. in the UK. Let's absolutely just have a good discussion with it. So today I'm going to be talking about a set of tools that I use to study how the brain, a complex system, deals with music, a complex stimulus. So my hope is to present the tools in a way that connects with your own work, because while I work on music and the brain, a lot of these tools are more generalizable than that. So the tools are important, very relevant to the study of dementia and aging and brains, but this is kind of a sneaky computational modeling talk. So I'm going to start off with why this is relevant. I'm not sure if anyone else has ever been a person on the internet before. We just got this in Canada. It's great. But if you're me and you work kind of in the music and art space, chances are your aunts on Facebook will start sending you these videos that come up every so often. A person with dementia, and they either have a headset popped on them or are listening to music, and then they just kind of come back into themselves a little bit. And these are people with kind of more advanced or severe dementias. And so you'll see people kind of singing words to songs, dancing, kind of remembering choreography. Like the lady in the vertically striped shirt down here is a ballerina and is kind of doing the choreography to Swan Lake. And just really kind of snapping back into, if not lucidity, then certainly more lucidity than you see before the music starts. Clinically, this phenomenon is known as really, really excellent. It's fantastic to see. And in my clinical work before I was a scientist, I used to see this relatively frequently. And there's a lot of unanswered questions here. So a couple of weeks ago, we heard from Dr. Angela Carter on this series on the underrepresentation of people with advanced dementia in research and the possibilities and challenges of working with this population. So if you weren't at that one, definitely go take a look at the recording. It was fabulous. And it was a really good introduction to some of the limitations that we encounter with research tools in working with people with cognitive decline or language loss into dementia. And in biomedical research, we are even farther behind kind of qualitative, descriptive, and phenomenological research in this way. Most of our work is focused on a cure, a drug treatment, identifying who is likely to develop dementia, but there are many, many, many people who already have a diagnosis and are kind of out there living their lives and wish to contribute in research and definitely have things to contribute to research, but they're really underserved by the tools that we have. So music is still there. It is very accessible. It is very engaging in a way that a lot of research tools are not to individuals with moderate to advanced dementia. So if we think about things like interviews or cognitive tests, we can give someone a diagnostic category, a diagnostic label, and then we can kind of conceptualize, where their language is at or how physiologically they're moving. But a lot of it is still dependent on language, and that doesn't, again, always work with linguistic and cognitive decline. And this is where the relevance comes in. So where music is a complex cognitive behavior and people with dementia have been shown to maintain very strong connections to music, and music does a lot in the brain, and there's a lot of research on this, and remains enjoyable and accessible to people with dementia, then why aren't we all using it, and what can it tell us about how the brain deals with dementia? So a little bit about me, who am I and what am I doing here? I got started in research the same as anyone else. So I was after a career in classical music, but then I got into music therapy as a way of kind of bridging this kind of like, well, I really enjoy being a performing musician, but what I really enjoy is kind of that human connection with music. And fortunately, the uni had a really good music therapy program. So I majored in music therapy and in classical flute performance. And then I worked for 4 years as a music therapist, mainly in long-term care. So I had a caseload of approximately 200 clients in residential long-term care, mostly with moderate to severe dementia. A lot of my clients were nonverbal, and they had kind of taken a step back from other programs, so they were referred to music therapy. So music therapy to computational neuroscience is not an obvious trajectory. But while I was a therapist, I was running into these frustrations with, not being able to describe the hows and the whys of why I was getting these really good results with my clients. I mean, clinically, it is enough that we have a benefit to our clientele or to our patients. But then people were constantly, it's like, well, your funding is up for review. Can you prove that this works? And I was like, well, not really. We don't really have the tools to do that. And it's like, well, if you can put a number on it, we can guarantee that you might have a job again next year. And I was like, Christ's sakes. So trying to figure out a way, and then the families too, which was a lot more compelling, would come up to me and be like, listen, we haven't heard our loved ones speak in months, if not years, but suddenly they're singing words to you. Like, how is that working? And I was like, oh, I really don't know. I really wish I did. And I figured that someone would have looked into it already, but it turns out that this is a really kind of area of research that, many things are kind of touching, but not quite diving into. So I decided to go look into that. So after leaving my clinical practice, I spent 2 years in grad school in Finland, doing a Bachelor of Music or a Master's in Music Psychology, learned how to think about music scientifically. Another 2 years in clinical research in the UK. I worked for a music therapy clinical trial at Anglia Ruskin University and University College, Imperial College London, rather. And then I spent 6 more years in grad school. I came back to Canada and did a PhD in the University of Toronto and in psychology, where I majored in computational neuroscience lab. And then 3 years so far into this postdoctoral fellowship in Simon Fraser in BC. And folks, she's on the job market. So if anyone is looking for anyone with any of that, my DMs are open. So one of the ways, like when I left my clinical practice, one of the things that I wanted to do is figure out a way of putting a number on this really complex phenomenon that I was seeing at work all the time. And if you need a tool or to develop a tool or a way of putting a number on a thing, computational neuroscience and computational modeling is a great place to look. It sounds really complicated, but really what a computational modeler or a computational neuroscientist is just like, hey, that's a cool thing. Let's put numbers on it. So we have a lot of beautiful qualitative and observational data, but a lot of fields and funding bodies still make use of the numbers. And there is kind of like this push-pull between like, well, how much are you squashing somebody down by kind of conceptualizing them with numerical data. But the great thing about complex systems work is that you don't necessarily have to squash people down to numbers. You give them many, many, many numbers, and then we have delicious information out of it. So I've got a lot of rants that I could say about a lot of these things. I'm going to try to keep them short and keep to time, but if anyone wants to like really get into some good old-fashioned ranting in the discussion, absolutely. So if we're going to put numbers on things, let's start with brain dynamics. So computational modeling is useful because it allows us to capture the workings of complex systems. So the perennial question here is, what am I going to do with all these dimensions? So hopefully not a controversial statement, but the brain is a dynamic system. It combines regions into networks, networks into groups of networks, or repertoires, super networks, circuits. There's a lot of really cringy sounding vocabulary out there. And these groups of networks process incoming information and execute behavior. So for a while, the idea was that we could find essential brain areas for X, Y, or Z behavior, but this is rarely the case. There's a lot of regions that work together over time to complete behavior. And understanding of this whole kind of network structure, on the one hand, it does make the math a little bit more complicated, but on the other hand, it gives us more possibilities. And if we go from looking at the brain as, a series of agents or a series of nodes that all kind of work together and start looking at the networks of nodes as the smallest unit of measurement, then we have another layer of information and can start looking at the interactions between these networks. So here's from a review paper from a few years back looking at the neural correlates of social improvisation. And so there's a lot of stuff that's going on in something, in just the playing of music. So we have auditory processing, we have output monitoring, spontaneous creativity, and social interaction. There are a lot of pieces of the brain that are active here. And so if we really drill down and focus on one of them, we are still going to get information. But then what do we see if we maybe take this entire chunk at the bottom on auditory processing and look at how it plays with the other regions on here, the other networks on here? So a little bit more about networks in particular. A network is a collection of agents or nodes. So in neuroscience, these are usually brain regions or sensors, and functionally, groupings of brain regions that behave similarly over time or in response to stimuli or behavior are grouped into functional networks. But this is not unique to the brain. So an orchestra is a network. I'm the bioluminescent piccolo player down there. So in an orchestra, your musicians would all be your nodes, and then the overall orchestra would be the network. An ecosystem is a network. This consortium is a network. We are all individual people on our Zoom, but we are now kind of bound together from listening to this talk today. And then afterwards, we're going to kind of disperse and go back to our whatever it is that we've got planned for the rest of the day or the evening. But the important part here is that nodes in a complex system have their own spatiotemporal dynamics, and so do networks. So if a node is kind of subscribed to a network, or if a node is joined a network, then that network is going to have its own spatial dynamics and temporal dynamics rather as well. It's kind of a multi-scale architecture. So the shared property of dynamic systems gives us emergence. So novel combinations of nodes that can act beyond the capacity of the individual nodes. We all know this as the adage, the whole quite literally is greater than the sum of its parts. And so that is emergence in complex systems. So here we move from brain region correlates to network correlates. Like let's say we have a functional auditory network. How is that gonna play off with the other networks that we have? But how we actually put the number onto the thing, there's lots of ways of doing this. So if you're interested, state space literature is massive right now. And one of the tools that I prefer to use is hidden Markov modeling. So it is a way of dimensionality reduction in space to focus on time. So what we have in hidden Markov modeling is a high dimensional time series, so either regions or scanner nodes or what have you, on the y-axis, and then on the x-axis we have time. And so then what this will do is kind of boil it all down into a discrete categorical selection of spatial configurations over time. So we go from having like 200 regions of the brain to having 4 to 12 networks, and then we can look at those networks over time so that we don't have to squish it down in time and just focus on space. So what you can get out of this is the ability to quantify network behavior over time. So how often is a network occupied? How long is an average visit length to the network? What is the likelihood of transition between networks? How fast are we transitioning between networks? Criminally under-explaining the math there. So if you really want to get into it, please give me all your questions at the end, and we can get into it. So with hidden Markov modeling, you get spatial states of the brain like this. You have them over time, and then you can do computations with them. Important side note, and a thing that I feel doesn't get the oxygen it deserves, is that naturalistic stimuli like music are very informative. So I'm not going to talk in depth about this work today, but again, if you're curious, we can get into it a bit later. Music can be network estimated. Motion data can be network estimated. And if you have a high dimensional time series in your data, it can be network estimated. So this is from work that we published in 2025 on EEG and naturalistic music listening. So we took the musical signal, wrung absolutely every piece of data that we could out of it using music information retrieval, ran that through a hidden Markov model estimation, and then got musical states the same as you would with brains. Now, we don't get nice pictures of brains with music. We get something that looks like a principal components analysis map where we get to go back and look at it. And just to give you an illustration of what that looks like, this is an example of these music features over time. So pay particular attention to that big red blob in the middle. Something is going to happen there.
What a voice, what a voice, what a voice I hear. It's like the voice of my beloved dear. But if I had wings like that swan, dear. But if I had wings like that swallow high, I would clasp in the arms of my belly boy.
All right, and that's just one example. That is a piece of music that you could listen to on whatever media people choose to listen to. You know, it's not illegal. You can find music and listen to it. And there's so much in there that we can then, look for in the brain. Is the brain tracking these things? Is it coming up with expectations? Are the expectations being met? Is it surprise, or are we reminiscing while listening to this music? Do we know any of this song? So yeah, so much to, again, put numbers on. It's a bit of a theme with me. So some of the open questions I had when doing my doctoral research was, can we use statistical modeling to estimate a music listening network space? So can we have a look at all of the possible brain configurations and kind of map this out with statistical modeling? Can we interrogate between network activity in this space at multiple temporal scales? So kind of listening being hierarchical, there's going to be different temporal scales. Like you can hear the timbre of something a lot faster than you can hear, a regularly occurring pulse. And are there network level differences in music listening related to age, behavior, clinical status, or the music itself? So the first thing I did was, this was during COVID. So fortunately, wonderful collaborator Psyche Louie and her group were able to send me some data. This is from a group of older versus younger adults listening to self-selected versus experimenter-selected music. And ran a hidden Markov model analysis on it, got 4 networks out of the music data, out of the fMRI data. And we found 2 that were particularly interesting. Network 2, bilateral auditory cortices. People are listening to music. The ears are involved. Yay, Nobel Prize for us. But then we had another bilateral auditory network down in network 3, but unlike network 2, network 3 had temporal mesolimbic regions active in it, which is great. So there was a stimulus effect, particularly between the temporal network and the temporal mesolimbic network. And what we kind of interpreted that to be as an auditory network and an auditory reward network. So when people were listening to music that they selected themselves, so these were highly familiar, well-liked pieces of music, their brains spent a lot more time in this network configuration of network 3, or network 3 was a lot more active. When they were listening to the music that the experimenters selected, they spent more time in this network 2, so they didn't get that temporal mesolimbic. They didn't get that mesolimbic kind of reward network type of activation. They weren't showing that. It turned out that this was gated between younger adults and older adults, because we also got them to rate their liking and familiarity of the pieces of music. So with younger adults, there was a clear effect of preference. Whereas older adults were more ambiguous. So there was a really good relationship in younger adults, but then we found with older adults, and these are healthy older adults, they do not report any diagnosis or any concern about memory disorders, but their brain dynamics were different. So it could be evidence of some age-related dedifferentiation, or a process where network activity and behavior becomes less finely tuned to specific stimuli, which was really interesting. And the transition between networks also showed this pattern. So for younger adults, they were much more likely to get in and stay into this temporal mesolimbic network with music that they liked and that was highly familiar. So the older adults, like the younger adults, were just like, great, thank you very much, captive audience full of undergrads in psychology courses. But the older adults stayed on for an additional 8-week music listening intervention. So they listened to music actively for about an hour a day, I think, for 8 weeks. And then they would have a once weekly meeting with a music therapist, or they would talk about any, thoughts, impressions that came up. They would alter their playlist based on what their needs were. And then we found post-intervention, the temporal mesolimbic network was even more active than it had been before. So for all types of music, we see that this temporal mesolimbic network is more active. Even if it was more active than younger adults pre-intervention, post-intervention, it was even more so, which showed really interestingly that with training, the network dynamics were shifting in older adults, which is kind of cool. It's kind of comparing apples and oranges here, but it's worth looking at. It's like we're not necessarily with music-based intervention making a pattern identical between younger adults and older adults, but it's kind of an interesting framework for aging and neuroscience and dementia research. It's like, are we trying to get a young pattern back, or are we trying to, roll ourselves back to the last kind of like major configuration shift, which is, something I spend a lot of time thinking about. The brain never stops developing, which does make the math a little bit more fiddly, but not impossible. So we can use statistical modeling to estimate music listening network space. We can interrogate between network activity in this space at multiple temporal scales. And there are network level differences in music listening related to age, behavior, clinical status, and music, which is super neat. And that's where we get back to dementia. So we know that the stimulus is engaging to this population. We know that they can engage with music and that it is very rewarding to them. And we know that music is also engaging to healthy adult populations, which really, really, really helps for comparison. So there are definitely still challenges. Again, biomedical research has been really slow to adapt these more naturalistic, ecologically valid measures. So we spend a lot of our time kind of writing and pausing. Actually, if you're running this big data collection for hundreds of people, why not add a music listening task just to see? But what really kind of keeps me motivated is that music gives us a way to make connection with a diagnostic group of people for whom connection is not straightforward anymore. And then these tools, these computational tools, gives us the means to measure this connection in a way that hopefully can then inform the research. Because if we understand what the brain is doing with complex stimuli, in addition to its adaptations around dementia, then that might help us with some of these other goals that we have as researchers. How does dementia work? How does it progress? And then what can we do with that? So if you would like a lot more information on any of this, please do check out the papers. They are all here, including a recent review with a consortium that we have between Canada and the UK on music and dementia care. I put the EEG paper in there. I didn't really talk about it much, but it was an absolute bear to get published. So I really like bringing it up. And there's another one of these talks that's coming up, which are probably going to have some similar themes. So stay curious about this. Thanks so much for being here. Really, really, really appreciate it. And let us absolutely be pals. You're more than welcome to get in touch at any time. You can find me over email or on the social media.
You caught me out. You were quicker than I thought. But thank you very much. That was it. That was amazing, including the musical interlude in the middle. Thank you so much. So just a reminder to everybody watching, you can ask questions now. We've already got a couple, and I've got some myself as well. But let's put our guests first, and we'll take our first question, who comes from Angela. Who you mentioned Angela's talk at the start?
Yay! I'm so happy you're here.
Thank you for a fascinating talk and for the reference to my presentation last week. Could you explain the different type of information that can be collected about aging, dementia, music, and related mathematics using different types of scans or other instruments? Do studies often mix types of scan to build diverse information, or do they generally stick to one type?
Yeah, this is super relevant. And with music and neuro research, we generally collect multiple types of information. So the big one is the brain and the behavior. So the brain, so I have used fMRI data before. MEG is something that we have here at the university that we can collect. And then EEG is what we kind of prefer when we're going out in the community. Just because the scans are portable, you don't have to bring someone into hospital to get an EEG scan done, whereas you do with fMRI and MEG. So it is possible to combine the imaging modalities, but we kind of generally start from like, okay, what's going to be less stressful to the participant? And then the behavioral data that we would get would be things like ratings, if someone is able to give verbal ratings. It could be bodily cues as well. So a big one that we have is I'm working with a data set from a group of collaborators. It's just resting state. So they're not doing anything. They're just sitting in a room, kind of pairs of people resting with each other. But we have brain data, eye tracking, smiling, and then body position. So like, are you leaning in together? Are you kind of like metronoming each other back and forth? So we absolutely try to collect as much as humanly possible. And then there's the data from the stimulus itself. So all of these things together can be informative and can tell you about kind of like slightly different angles of things. So the behavioral data from the fMRI stuff that I showed from Psyche's group, the behavioral data was useful because then we could sort the brain data into different bins. And we're like, okay, here's all of the brain activity when people are listening to stuff that they really love. Here's all the brain activity when people are listening to stuff that they absolutely hate. And then here's all the rest of the stuff. Is there any difference there? So it's just kind of like different ways of slicing the data.
Thank you very much. We've got a load of questions. Let's take our next one. Do you think music is a special case for probing brain dynamics, or just a particularly convenient one?
Oh, yeah. I'm going to do the classic psychology thing, and I think it's both. So I think it is a special one because it does a lot of things that other higher order cognitive behaviors like language does. But unlike conversation, we're not expected to kind of give back in the same way. So a big thing that we hear about when working with, so I work with the local Alzheimer's Society in British Columbia here, and they are absolutely fantastic with people with lived experience. So they have lived experience experts, so people with dementia and their caregivers who work with researchers to help us make sure that we are working well with their community, answering questions that they want to ask. And then crucially, they can also write letters on our behalf to ethics commissions that are like, let us participate in research, it's fine. Super helpful, by the way. And so one of the things they bring up is when someone starts, like with a diagnosis of dementia, kind of starts to decline a little bit, one of the biggest things that they bring up is communication becomes really problematic. And so it can kind of like get into these patterns of either monologuing at a person or kind of almost like a quiz master type thing where it's like, do you remember this? It's like, what were you wearing when we were doing this? Whereas with music, you can just kind of put it on or like listen to music together. And you don't have to do anything, but your brain is still doing a lot. So it's like it's both convenient and special, because if you're listening to music and you have dementia, and you're listening to music and you don't have dementia, there's not a heck of a lot that's at the surface level super different.
Thank you. Let's take the next one, because we've got a few to get through. You mentioned these tools are generalizable. What are the key assumptions in your modeling approach that might not hold outside of music?
Yeah, this is fabulous. The big one is an external time course, like a feature-rich external time course, that we can use to contextualize the brain findings. So in music, we have, again, the temporal time course, we have all of the features that we can get out of music, and then we have the entire field of musicology, computational musicology, and music feature extraction, to really inform kind of how we boundary select what our significant events are in the music.
Yeah.
We see this a little bit in studies of language, especially conversation, or in like storytelling, where it's like you have certain words or phrases or kind of like divergences where in English, like verb, the adjective, noun, it's like we're waiting to get to the noun. And so like this kind of is a load bearing part of the sentence. In movie watching, this is something that I've had lots of creative discussions with some of the lovely people who do naturalistic movie watching. There is less of a tendency to embrace kind of artistic sensibilities into how they break down the salient events in a film signal, and it's still at a point where we're kind of like averaging down loads of things to look at spatial configurations. So one of the things that I encourage people to do is, if they are doing task-based work, really dive into the properties of that task or the stimulus that you're using itself to see if it has anything temporally to reveal, because those can be super useful as, again, like anchor points to look at the brain data. Now, resting
Yeah.
state, not much, but yeah.
Have you done this same work with movies?
Mm.
You tried, it's just in your field?
Yeah, not personally. We do have a group of people that are at the next university over that are really big into the naturalistic movies. And so what they've actually started doing is working with filmmakers to create purpose-built movies for research, where they can kind of manipulate these parameters.
Interesting. Yeah, well, almost like a choose your own adventure. You just
Yeah.
will adjust the next scene based on what we've had so far. Which actually, that brings me on to a question that I had, which is, what features of music are doing the heavy lifting? Is it the rhythm, the harmony, the prediction error? Do you see differences there?
Yeah, and again, it really super depends. So there's like the two biggest group of features that we see are low-level features and high-level features. So your low-level features are kind of context-free. They describe the kind of timbral quality of the sound. So it's like an example of a low-level feature is, if you're listening to someone's voice, you can tell pretty quickly if they have a cold. If you listen to them a little bit longer, you get into high-level features, and that's how you can tell, like, oh, do I recognize this person? Does this person have an accent? Or if you're listening to, a piece of dance music, a high level feature would be your rhythmic predictability. So like, is there going to be a beat drop? Is the beat kind of getting faster and faster? Are we getting to this point where we have, the building of expectancy? And then for timbral stuff, it's kind of like you would find with a spectrogram. So it's like voice recognition, or even stellar mapping, where you have these like light frequency spectra. You can take a look at a spectrum of a musical signal, and then you can kind of like, okay, there's a lot of stuff concentrated in low frequencies, and then there's a little bit in high frequencies. Am I listening to something that's super bassy? Or it's like, this is a lot of high frequency and like a little bit of low frequency. Is this a boy band? Those are some of the timbral stuff. And then the different genres of music will have their own kind of high kind of higher order feature convention. So like folk music is generally a little bit more cyclical, and you need to pay more attention to the lyrics rather than, let's say, like metal music, which is like super rhythmic, but will have kind of like these different chunks of music.
Oh, that makes sense. Right, this is a long one. Regular watcher Jack, thanks for joining us, Jack. Always reliable to turn up. Note 1, through plasticity, is higher though plasticity is higher in younger adults, we tend to grow more attached to preferences at that age, cliqueness. So there is a multifactored approach to nostalgia, whereas as we age, nostalgia becomes more intimate and quietly enjoyable. Some of us get stuck in our ways musically, but many of us will then spend time searching for a new music and actively comparing it to our tastes, appreciate the quality of music and the measure of it, which actually is a good... for those who are watching, you either know or you don't know, but I ditched fantasy football this year, and instead I'm in the music league. It's a thing that ties up with Spotify, and every week the guy, Dave Cash, hi Dave if you're watching, runs the music league. It's all neuroscientists that are in this music league, and they set a theme every week. So this week's was a song that will inspire you in spring. And then everybody submits a song anonymously. Then you have to give them your points. You get 20 points to allocate across, and whoever's song wins. It's a music league. I can invite you if you like, Sarah. You can join halfway through. Anyway.
I'll be looking this up.
It's a way to force you to listen to different music. You have to, but I'll invite you if you're interested. His question though: do the effects of key BPM genre vary substantially across subject? And are people living with dementia, are their pre-dementia music tastes aligned with the therapeutic tone songs? Good question.
Yeah, so when we talk about perception, we can kind of get at this a little bit. Now, the gear does let us down a little bit. So in fMRI, you can see very, very finely tuned, regions of the brain. But then your temporal, like your ability to make conclusions over time goes a little bit further down. Whereas with EEG, you can, like the brain data can be collected at almost as high a frequency as the music data. So you can line it up over time super precisely. But then you're kind of compromising on the spatial resolution. So, and I forgot to answer the second part of your initial question. So yes, there is individual variability in how you listen to music. So the two big ones that we see in a group of people, and this might be fun to think about for yourself, is if you listen to a piece of music, if you listen to the lyrics first or the music first. I play in a band, and sometimes there's songs that I've loved for years that I don't understand that the lyrics are absolute trash until I go to sing them. And I'm like, oh yeah, no, this is bad. So yes, there can be individual differences in what you prioritize to listen to. Whether or not that looks the same in the brain is still kind of up in the air. So musicians generally tend to focus in on bits and pieces, and it might be, there are structural differences in the brains of highly trained musicians versus non-musicians. This might then lead to functional differences, but it's a bit of it's not 100% known right now. And for dementia, your musical preferences from that kind of reminiscence bump area when you're in your late adolescence or early adulthood, regardless of what kind of, amazing stuff you were listening to at the time. I'm kind of going through my mental catalog, and it's like, I don't know if I want them to play me a bunch of Spice Girls in the nursing home, but I will probably have a good time if they do. It can be a really useful starting point for people to kind of revisit that stuff that was popular beforehand. But again, that relies on being able to talk to someone or knowing, where they grew up, exactly how old they are. So these things are really tied to time, and they're also tied to location. So the stuff that was popular in Canada, because of our wonderful CanCon laws, where we have to play Canadian music on the radio to prevent, the market becoming completely saturated with American music, might not be the same as in the United Kingdom.
Probably not. Let's take our next question. How sensitive are the results to choice of model parameters or priors? I don't understand that question. I hope you do.
Oh, yeah, absolutely. And this is a great question. Thank you so much. So the results, like the choice of model itself, as much as they're really helpful, they can be a bit clunky. So hidden Markov modeling, there's a lot of different flavors to that. A lot of the parameterization is driven by the modality. So fMRI will have not a completely different parameter estimation set of parameters, but it will have a reasonably markedly different one than if you're using EEG or MEG or something with that higher temporal resolution. So it can affect the output that you get, but there are ways of mitigating this. So the biggest change with what you get in hidden Markov modeling is just the states So like the spatial patterns or the spatial networks look different between subsequent estimations. So what we can do for that, there's a great tool called Status, which I will post here in the chat, which is structuring of three-way statistical tables. It's French. And so there's a lot of sources in French on it, but very slow to be adopted in the English-speaking world. So there's one guy.
Canada, then.
So Abdi and Valentin are the two people to look at for that. So it's essentially a way of taking correlation matrices or similarity matrices or dissimilarity matrices, lining them up in a third dimension, and then coming up with like a singular value decomposition type way of comparing between them. Initially, this research was for taste and wine ratings. And so it's like, well, how people think about wine and beer taste is extremely subjective. So let's put numbers on it. Again, back to the theme. So then the big thing is making sure that you're confident with the estimation of hidden Markov modeling, which is just a lot of back and forth. It's like you run the estimation, you look at it. You run the estimation, you look at it. You run the estimation, you look at it. And then when things stop being quite so volatile, then you're like, okay, let's proceed now with the analysis. And I didn't mention this, but the biggest statistical tool that we use in our lab is partial least squares analysis, which again is based on singular value decomposition. So it can sometimes it's like bringing a machine gun to a knife fight. We don't have to use PLS for everything, but it is extremely kind of conservative, and it doesn't fall into a lot of the traps that you do with like highly dimensionality complexed on one dimension, but yet dimensionality reduced data on another dimension. With bootstrapping and permutation testing. So inside the test itself, it fixes a lot of the problems that we see with like univariate methods.
We've got a lot of questions to get through and not enough time. So we're gonna you got speedy answers now. Are you ready? Because I want to try and answer everybody's questions. So let's go through speedy. Do you see consistent signatures across individuals, or is the variability itself part of the signal?
We see both.
Okay, well done. Next one. Do your models distinguish between adaptive reorganization and pathological breakdown?
They do not. For that, we have to look at other types of information.
Okay. How do you validate that patterns you're seeing reflect meaningful brain function rather than model artifacts?
By being extremely, extremely, extremely careful, running things from a lot of different points of reference. And then from like null models are really helpful as well. Yeah, so it's like, can we generate these randomly? If we can, then we have a problem. So that's again where the permutation and the bootstrapping really come in handy here.
Yeah, I am going to look at the ones in the chat as well. So don't worry if you've put your question in the chat and not in the Q&A. Next one, Jack's got another one. I suppose a lot of time frequency domain work would translate well from EEG recordings to music therapy, voltage versus time, air versus pressure, etc. Have you tried any other supervised, unsupervised machine learning techniques or dealt with the measure of signal complexity in these networks? Example,
we haven't with the networks, but with the actual regions. We've done a lot of multi-scale entropy work in the lab. And so there is this like multi-scale entropy interaction in aging and dementia, less well understood between kind of like healthy aging and dementia. So I'm really, really, really keen to get into that directly with a population with dementia, because what you can do is you can also take the multi-scale entropy curves from the time series of the music features, and then you can do like a complexity matching between the curves using something like Procruste's distance to just like look at like, oh, how is this bumpy line similar or different to this bumpy line? And then that's kind of like an index of how people are tracking the stimulus. It doesn't help if the stimulus becomes decoupled. Like if like someone starts reminiscing and then kind of like gets lost in the reminiscence and stops listening to the music, then we might see a little bit of a breakdown, but that's science.
It's that sensitive though. Okay, Angela's got a question. Would you mind talking us through what was happening in more depth during the music example you provided, please? I'm watching this on a tiny screen. So you're watching on your phone, Angela.
Yeah, so this is just a piece of music that I really like. It's called Blackbird by Martin Bennett from the Grit album. So it was a phenomenal Scottish musician who sadly passed away very young, but would do a lot of this kind of mixing of traditional Scottish recordings with like modern electronic dance music, which aces. And then Greg Lawson.
I remember that piece of music because it was used in it's been used in a TV advert, a really big TV
Porridge.
advert, and I can't remember which one though. It will, I will remember.
There was one of his songs was used in a porridge oats commercial.
I can't remember. It might have been an advert for the fjords or something like that. Like take a fjord cruise.
Yeah. So this
sorry, I believe you answered the
doing
question.
like feature extraction on music. You should probably pick a song that you really like listening to, because you're going to listen to it a lot of times. So this was a song that I really liked, and this is an example of all of the different features that we get out of the music feature extraction. So Alluri, I will write it in the chat, Alluri and Toiviainen and others kind of started pushing this work of looking at like really deep feature extraction in music, and then taking those time series and lining them up with brain activity and whole brain recordings to see, again, if we could get that like nice tracking between individual features in the music and regions or kind of like temporal interactions in the brain. So what that was is just looking at all of the things that I get out of a musical signal over time to kind of like start us thinking about how much there actually is in a musical signal. Because of course you have the very quick context-free things of like when new information or when new instruments come in, versus the longer scale thing of when we hear that kind of big and it's like expectation is building. So that's a bit of a longer thing. It's like there's a women's voice here and then there's a men's choir up here. And so if we sit there and like really listen to the music that we listen to, and like being a trained musician, this is something that comes baked into the training. You have to listen to things across multiple dimensions, because there are minute adjustments that you make to alter your pitch or your articulation, but then there are also longer term things that have to do with the interpretation of the piece or the phrasing that you're doing. And so this is something that comes naturally to those of us who have musical training when listening to music, but then again we have to be able to make a computer do it. Otherwise it's not replicable. But I think my old theory professor would have something to say about that.
But you can see it though, can't you? You can see, I mean, I love when you get that kind of stacked data and it really, really beautifully visually represents what is happening, and being able to kind of plot that data and temporally align it to a tune as well. And you can see how the brain lights up at different places is really beautiful. Yeah. Okay, we'll jump into the chat as well, and I think we've just got one last one here to bring up in the chat, which I will do. Olga says there's a misdiagnosis by caregivers that act like bullies to neurodiversity. Music is liberating to a process that moves patients from out of trauma-induced aphasia to, for instance, revealing muscle exercises and brain muscle tissue rehab. Thanks very much for the maths cues, Sarah. It is very good.
Oh, pleasure. Well, I'm really hopefully, because the thing is, it can be difficult to kind of bring all of these fields together and explain to them why they should kiss each other a little bit. So kind of like coming from this clinical background and then saying like, hey, it would be really useful if we could take all of what we've learned from over here and all of what we know already from over here and kind of fit them together. Yeah, I figured it would be relatively straightforward, and that was like 12 years ago. So it's going to be the next however many years.
I mean, as you say, when you're trying to influence policymakers, funders, that beyond the kind of anecdotal of I remember we did a podcast on this, our Minds in Motion series, and we had Trevor Salomon on there saying how how his wife, when she was getting worse, that the days when they went to the kind of singing group and the music group, you knew that when they came home she had a much better day. But that Trevor's perception of his wife being better on the days when she had that activity or did that thing, as opposed backed up with what you're discovering here through these mathematical models, is hopefully far more persuasive to
about persuasion, because I really love this work, but I do think that there is a tendency, like what gets incentivized nowadays is this kind of hard science type stuff, and it's the information is no more or less valid because we've run it through I've written a fiendishly complicated computer program to do it. It's like, this is what people are saying. And so it's like, it's just being able to translate the information to as many people as possible, I think, because there are people where I start kind of going on about the mathematical stuff and it's complete glazed over. It's like, just give me a caregiver telling me that their loved one is better and I will believe you. And it's like, oh, incredible. Here, like talk to this person. But it's like the people that need, yeah.
The people funding, yeah, exactly. It's a a tough world out there at the moment. Having everything that you've got available, whether that's the caregiver, the modeling, the maths, whatever it is, to make the
Yeah.
argument and the case for what we know is a good thing to do, I think is really important. Thank you so much. Incredible, Sarah. This is only the second time you've been here, and it's fascinating every time. You're welcome back every week. Pick on a different subject next time. We want to hear from you more. We're going to be back, though. That's all we've got time for today. But we are going to be back next Wednesday at 12 noon that time. So that's Wednesday, the 5th of April, when we're going to be joined by Dr. Rachel Allen, who is going to talk to us. Well, let me give you my blurb. Rachel from the University of Western Scotland is going to present her work on working with Dementia Network Plus project, exploring how dementia and employment across research policies and practices, and looking at their nominal group techniques and their focus group work to see how you can continue to work post-diagnosis, which is important. Thank you so much again, Sarah. We'll look forward to seeing you again. And if you have anybody who's got any questions or wants to follow up, Sarah's available in the community. Drop her a message.
All right. Thank you so much. We'll see you again.
Thank you very much. Have a great evening. Bye-bye.